I start my recording now, and people can be added later. I don't know because it's already 10 minutes, right? So here, Zoom.
All right.
Screen 1, 2, 3. Okay, so we officially finished chapter 1. Okay, is there any questions so far from chapter 1? If it's the case, I can tell you that we are starting chapter 2, which is Boolean Algebra. End of the chapter 1, you will find that it identified to you gates, and those gates we have in the digital logics are OR gate and gate, not gate, and then combination between an OR and NOT gate, you have NAND gate, and then you have a combination between OR gate and NOT gate, you have NOR gate, and then you have the combination between AND and OR and NOT gate, you're gonna give you XOR gate and XNOR gate. This is very important topic. Why it's important topic? Majority of the part here is going to be manipulations. How can you play between gates to change from one to the other? Okay, but before I do this, I would recommend going first to the Boolean algebra, fully understand what is Boolean algebra, and from there we will move to the gates. That makes sense? Okay, so what is Boolean algebra? So basically, we said that we have a binary system. Computer's binary system. What does it mean? That means if I have a certain variable, which is called x, so that means that variable can hold 0 or 1. That's it. You agree? So that means it cannot hold more than that. It's just two options. So if you have a system, like a block like this, and this block has x as an input and y as an input, and it have a z as an output, so pretty much I can write the transfer function of this as the following. I say it's a function of the x and y, and this is equal z, right? What is this function? I have no idea, but at least I would describe a situation now. Say that, this graph in front of me, it has both x and y are input, going into transfer function and producing z. How can I write it in equation like that? Right? What is exactly this function is doing is not that important now. Okay? Now, there is some tricks you need to know about the Boolean algebra before we do anything. So imagine that you have x, y like this. X, y, right? Let me tell you a story about this sign thing, right? OR gate, just put it like this in your hand. OR gate, the sign of it is positive like that. So it's no longer called adding, it's OR. You know what I mean? So this is OR gate. Then there is no longer multiplication. It's called what? AND gate. So you are ANDing or ORing. Let's give example, right? So z as a function of x and y is x ANDed with y ANDed with z. Let's be more dab. So what I'm saying is no more multiplication. There is no multiplication. That's called Boolean algebra. You know, we are learning now ABC of something else. It's not and or. Sorry, it's not add and subtract or multiply. Okay? So now we have what? This is very obvious. We have X added to Y, and that thing will be added to W. So the same rule we learn while we are learning math. Do you remember? So basically this is equal to what? X added to Y added to W, I'm sorry, and this will be added to Y. So that means you can distribute. Okay? Okay. Another thing we need to learn. Z is equal fxy, and the value is x added to y, and it's not added, I'm sorry, or to y. Yes, and that will be what? That will be added to w. So that means you can distribute. What does it mean? So that can be x added to w, or with w added to y. Right? This is something we have to put in mind. No longer, while you are talking about digital logic, you are not talking about add and subtract and multiply. You're talking about operations, which is ending or oring. Or let me tell you the other trick, or not gating. Not gating, not gating. What not gating mean? That means you're using the not gate. Okay, an example for this. Z as a function of x is y, it's gonna be x. Here's the sign of the not gated or complemented. So that means, you know, if x is 0, that thing it will equal what? 1. That makes sense? So if x is equal 0, so z it will be what? The complement of 0 is 1. Right? If x is equal 1, z will be the complement of 1, which is 0. So far, so good? So now we have the aspect of or, we have the aspect of and we have the aspect of the not gated. Is there any questions so far? Those are basics. Those are very important basics. Now we need to learn some of the stuff which will help us to how to say, to simplify equations of the Boolean algebra. I'm sorry, what happened? So let me see. So what is this thing? So imagine that somebody's telling you x is ORed with 0. X is ORed with 0. Or x is ORed with 1. What the output can be in this case? X is ORed with 0. X is ORed with 1. What the output will be in this case? X is ANDed with 0. X is ANDed with 1. What the output will be in this case? This stuff we need to know. They're going to help us in simplification. Okay? So let's imagine that, you know, we don't know anything about digital logic, right? So we're going to come in here and say that if x is equal 0. Do you agree? I can go ahead and say that mean 0 ORed with 0, right? Output of this will be what? If 0 ORed with 0, 0. Then if x is equal 1, so that means 1 ORed with 0. It is like kind of adding, but you are not adding. That's called Boolean adding, okay? So that means 1 plus 0 in your head. What is this?
1.
1. Have you noticed something? The x giving you the same outputs. So pretty much you can actually write this as what? X. Right? So you can come and say x ORed with 0 is equal x. Do you agree? Okay, now let's play the same game with x and 1, right? So if x is equal 0, output will be what?
1.
1. If x is equal 1, output will be what?
1.
1. Why? Because this not 1 plus 1 equals 0 in a binary. That's called Boolean addition. So in a Boolean addition, 1 plus 1 is 1. But in the binary addition, 1 plus 1 is 0. And you have a carry 1. That makes sense? So pretty much, I can write that gonna be 1. So no matter what is the value of x, the whole product will be 1. So I can come and say x was 1, or together, output will be 1. Make sense? Clear? Okay. Now, let's go to here. And from there, I will start defining some gates. X ended to 0. So if the x is equal 0, so it's going to be 0 to 0, what is the output will be? 0. It's like you're multiplying them, 0. If x is equal 1, so 1 to 0, so that means you're multiplying 1 to 0. So the output will be 0. So pretty much whatever the value of x it is exists, the output will be still 0. That makes sense? Okay, now same thing for the x with 1. If you have x and 1 like this, if x is equal 0, so it's going to be 0 to 1, output will be 0. If x is equal 1 to 1, if 1 ended to 1, the output will be what? 1. So pretty much you can write x ended to 1 is equal x. Those are very important for facts from the Boolean algebra. That makes sense? So we can, out of this, identify something is called truth. Yes. Huh? We can identify something is called truth table. Truth table. What is this truth table? So truth table in general, it is something we need to learn. Why we need to learn? Because it's really important to do in the design process till the rest of this course and even the rest of the digital logic in your whole entire practical life. So truth table, it's a 2 segments like this. Here we are sorting the input variables we have, while there we are sorting all possible outputs variable there. So those are not variable anymore, those is output functions. That makes sense? Again, any truth table, it's a 2 parts. Part sorting all the input variables we have, while the output functions will be on the other side of the line of the truth table. Let's have an example. So the first example, it's actually defining gates. And these gates will help us in the rest of the Boolean algebra story. Okay? Let's say, what is the basic gates we have? What is the gates created out of the basic gates are? So do you remember in the beginning, I give you a list of gates here? You remember those?
Yes. And
yes.
No. And
exactly. So I can use a different color and say that OR and 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 NOT gate, those 3 guys are the basic gates. Why? Because NAND is a combination between AND and NOT gate. Why? NOR is a combination between OR and NOT gate. Why? Because XOR is combination between all of those guys. Why? Because XNOR also combination between all of those guys. So if you fully understand OR and NOT, you are set. And by the way, those 3 guys are the most important element in the Boolean algebra. Okay? So let's take it one by one. So we said NOT gate. So NOT gate. Any gate, it's gonna be represented by 2 things. Oh, sorry, 3 things. What is the 3 things? truth table and Boolean function and symbol. What is those? Truth table, defining the relation between input and output, translating it to function, and while you are implementing this function on a hardware, you're gonna use the symbol representation. So this is used for the implementation. So if you have any question in the exam or even practical life, say that design a circuit, so that means you're gonna go from the truth table up to the implementation. Okay, so let's take the NOT gate. So the NOT gate is basically, we said it's flipping one input, right? So I can come and say I just have one input. So I open my truth table like this. And I imagine that the input of this circuit is called X. And I'm imagining the output of this circuit is called Z. Right? Then I need to think from my head, Professor Ali, I believe that, I need to know how many states this table will be in, right? So in that case, how can I do it based on the number of inputs? So X can be 0 or can be what? 1. So that means I have how many states? 2 states. A state that X is equal 0, a state that X is equal 1. I have no idea what is the output. Do you agree? Still, I need to see the output. The output from the functionality, I can write f as a function of x. So basically, x is input into the function. And can you see? I don't know what's exactly happening. 1 second. The zoom went off. 1 second. Can you see now? I don't know what is exactly happening here. So 1 second.
Not yet, Professor.
I think something happened. So just let me do one thing and I will be with you. I say this share and then I say stop sharing. Then I will go here and say that, Zoom is no longer sharing your screen. Okay, then I can go back into the screen here and say broadcasting. Then it might work. See? So yeah, we tricked the Zoom. Notability is being bad notability. Okay, anyway, so now, so Z, it's a function of X, and the output of it, it's X and what? Inverted, complemented. So the function here is describing the relation there, right? So from this function, I can fill the table, right? If my X is equal 0, so it's gonna be 0 complemented, so the output is 1. If my X is equal 1, so it's gonna be 1 complemented, gonna be 0. So what I did in front of you, I made a truth table for the NOT gate. Then I have to go and make the symbol wise. So the symbol is gonna be like that. And this is X and this is X complement. So this is something you have to put it in your head exactly like 1 plus 1 is equal to. Okay, so 1 plus 1 is equal to is exactly like this. You already have X, X complement for the NOT gate. Any questions so far? Any question?
Yeah, Professor, for your Boolean form, what does that say?
What's that? This one?
Yes, it says like X naught and then equals to, what does that say?
This one?
In Boolean? No, Boolean form right there.
This one? It's complement.
Yes.
You're talking about this one, right?
Mm-hmm.
That's complement. That means I complemented the X. That means I inverted X. Okay?
Gotcha.
Okay. Now we're gonna go into the OR gate. OR gates normally it works as 2 inputs or more. 2 inputs or more. Okay, so we need the OR gate, we need the Boolean algebra function, and we need the symbol. So now it is two input or more. So I'm imagining that I have 2 input. One is called X, one is called Y, and my output is equal Z. Before I touch anything in this table, how many states I should have? So the states is defined by the 2 power number of variables input. So how many variables in front of you guys? X and Y.
2.
2. So that means how many states I should have? 4.
4.
Why 4? I will show you. 1, 2, 3, 4. So 0, 1, 0, 1, 0, 0, 1, 1. So maybe if X is equal 0, Y is equal 0. Or maybe X is equal 0, Y is equal 1. Or maybe X is equal 1 and Y is equal 0. Maybe X is equal 1 and Y is equal 1. So you are covering all of the possible cases of both of them as an input. That's why number of states are the 2 power of number of variables. Sounds good? Now, the Boolean functions as an equation, it says that Z is equal f of X and Y because I have 2 variables are input of Z, right? Then if you guys remember in the top, in the Boolean algebra while I was talking, I said we don't have addition anymore, right? So that's basically, the OR is basically the addition of the Boolean algebra. So gonna be X OR Y. If X OR Y, and this is a situation, apply every single state in this one and see what will be the output. So 0, and you have plus in your heads, 0 and 0, so that means you already have 0. Any of them has 1, the output will be 1. And the moment we said the Boolean fundamental thing, if you have 1 and 1, the output will be not 0 and carry, it's gonna be 1. So what we did here, we use the function of filling the table we need for the OR gate. That makes sense? The symbol wise, while you're making implementation, look like that. X, Y, Z. And this is how it looked like while you are drawing your circuit for the OR gate. Okay? So now, so far we learned NOT gate and we learned the OR gate. Do you agree? So the third basic one we need to learn is the AND gate, right? Same thing. AND gate has the same story. The minimum number of variable inputs which we could have is actually 2. So in that case, I'm gonna make a truth table like this, imagining that I have inputs called X and Y, and then 1, 2, 3, 4. And here is my Z. We agreed together that, you know, that's gonna be 0, 1, 0, 1, 0, 0, 1, 1, right? Then equation wise, it's gonna be Z is equal f of the X, Y, and X like this. And we did this trick, if you remember when I said X ended with 0, X ended with 1, and so on, right? So in that case, if I would like to fill my table, I will just play the trick. If any of them 0, I'm sure the output will be 0. So the only thing the output will be equal 1 when both of them exist with 1. So here is gonna be 0, 0, 0, 1. Right? And the symbol wise for the gate, it's gonna be what? Like that. What we did today is actually learning the most 2 valued Boolean algebra function or basis gonna be used for drawing and helping the optimization process for the circuit. Okay, now using all of these guys, we can learn some tricks, and I can show you the trick. Let me see what I can do. What do you say? Could you go back to Notegate when you get the chance so I can snap here? Yes. Can you see Joseph? Okay. Okay. Now, let me show you something. Look at this. X, y, right? Ended with x, z. Look at this. I would like to see what is the optimization we can apply here based on whatever we learn, right? So look at what we're gonna do. We can just like, basically like multiply and adding and all these things, right? But algebra wise, we're gonna do something. So it's gonna be a function of f of x and y and z. Now we're gonna be x ended with x, right? Then ORed with x ended with z. Then ORed with x ended with y. Then ORed with y ended with z. Do you agree? Okay. If x ended with x, what is the output expected will be?
Either
X.
0 or 1.
Yeah, I mean, you try, think about it. If you put x is equal to x, and you end them together, the output should be x.
X.
Do you agree?
Yeah.
If you are not agree, we can see. So imagine if we take it out like this, x, right? And then, we decide if x is equal 0, so that means 0 ended with 0 is 0. If x is equal 1, 1 ended with 1 is equal 1. 1 here, output is 1, 0 is 0, 0 is 0. So that means I can completely remove this term and replace it with what? X. Super easy, right? Now, we need to look to something different, which is what you have here, x with y, right? There, you can actually take z by itself, right? And you will OR it with the x, y. Can you do that? Right? So now there is more fun. Why? Because, this term can give us something, right? So what is this something? It can be x ended with 1 ORed with y, like this. And then you already have z, x, and y. Do you agree? Right? Look at this. 1 ORed with y is what? We already did it up. You remember?
1.
1. Why 1? Because, if y is equal 0, output is 1. If y is equal 1, output is 1. So you can just say this is x. Right? Still, we can do this trick one more time. Do you agree? This one with x will give us what? X. Right? Let's see. It's going to be x ended with 1 and z. And you already have here z, y. This one is what? 1, right? So pretty much you can come and say this is x ORed with y ended with z, and this is the output. So pretty much if you would like to play and manipulate systems, you can replace this to be what? Equal to x ORed with y ended with x OR with Z. This one is equivalent to this one. Make sense? It's a lot of fun, right? You guys have any question? Now, let me find you some more tricks. There is something is called postulates and theorems under Boolean algebra. Quickly we can learn. And we already mentioned that, right? Like x ORed with 0 is equal x, for instance. X is ended with 1 is x. For instance, look at this one, which is fun. X ORed with x complement of it. So now we have an OR applied there, and we have a complement which is not get applied on the other one. What the output of this will be?
1.
It's 1. Why? We need to try, right? I mean, I don't know, maybe it's not 1. So if x is equal 0, so that means 0 plus, and this is 0 inverted, so gonna be 1, so the output is equal 1. If x is equal 1, so that's gonna be 1, and that will be 0, and the output will equal 1. So no matter what is equal 1, so pretty much you can come and say x ORed with x complement is equal 1. Right? Also, x ended with x complement, what will be the output? It will be 0. Why? We try.
Always going to be opposite.
Huh? So yeah,
They're always going to be opposite.
if x is equal 0, so going to be 0 ended with 1, 0, 1 ended to 0, 0. And those actually part of the De Morgan theorem. I will talk about it soon. Okay. So you need to know something which is x ORed with x complement is equal 1. You need to know also x ended with x complement is equal 0. This is very important. Very important. Sounds good? Okay. Now, everybody agree that x with x like that, it will be what? So this is equal to x, and it's 1 with y, and this is equal 1, so this is equal x. Right? Now, De Morgan. So what De Morgan says? De Morgan says if you have x ORed with y, and you complement it the whole entire block, what will be the output? Will be the reverse. So listen to this carefully, please. So if you have the complement and you would like to distribute the complement on the terms inside the equation, you will find out the following. You're gonna take the complement on x, and you're gonna take the complement on y. Then the complement on the OR gate, it will be what? AND gate.
Oh, snap.
Let's check whether that I'm saying something correct or not, right? So if we make a truth table saying that here's x and here's y, 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1, right? Again, I make a two output to compare with. One is x ORed with y complement, and one is x complement ended with y complement, and see whether those two guys are equal to the same or not, right? So if both of them are 0, 0 ended to OR to 0 is 0, you flipped it, it's gonna be 1, right? If one of them is 1, it will be 0, all right? Let's go on the other side. If both of them are 0, everybody gonna be itself 1 ended to 1, the output will be 1. If one of them, it's gonna make it 0. So conclusion, this column equal to that column. That's why De Morgan said that. So if you have a terms, the complement will be breaking into the variables and convert any or to and any and to or. Okay? Sounds good? We can play it with more variables. Let's say x complement, or with y complement, or with z complement, and ended with x complement, with w complement, and everything here is complemented. What should we do? We're gonna distribute, right? So look, so you're gonna distribute to what? First of all, x complement, or with y complement, or with z complement, and 1. And then, you know, ended here, it's gonna be what? It's gonna be ORed. Then the other one here is gonna be what? X complement, W complement, and you have here complement. Then you will go inside every one and convert it, right? So here, X complement, this is something I need to tell you, okay? If you complement the complement, what is the output will be?
X, just no complement.
Exactly. So any, you know, if this one is n and this n is even, the output will be what? The same. If the number of complement at the top of x is odd, the output will be x complement. Okay, so x 1, 2, 3, 4, 5, 6. What is the output will be?
X.
X. If x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, the output will be what?
X prime
It will
or
be
X
x
complement.
complement. Why? Count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 odd. 14 gonna make it x, number 15 will make it x complement. Make sense? Okay, so now we're gonna do the same trick. So we're gonna take this guys and break in there. So gonna be x complement, complement, right? And the or between of them will be and, right? So now is and. Then the other one is y complement, complement. Then the or between of them with z is gonna be what? And then z complement, complement, right? And then I take this one and I keep it as it is. The or is still there. I'll do the same thing with x. So gonna be x complement, complement, and then w complement, complement, and then I will move forward to make this one x, y, z, and it was x, w, right? Everybody agree? Any question? So in front of you, such a kind of terms, it converted to be this one. What is the best advice I can give you? Practice. Right? You will find infinity number of examples in the back of the book. And we have the book, a link posted on the Slack. Right? I didn't give you guys anything. Right? I have no idea about what is this link we are talking about. So those are two more De Morgan thing. And we already talked about it. So, okay, that's perfectly fine. No. Okay, so do you think x ORed with x is equivalent to x ended with x? Or this statement is wrong?
That's right.
It is right. Why? Let's try. We go from here. If this one ORed with 1 is equal 1, if 0 ORed with 0 is equal 0, so that means this equal x. Then let's go there. If both of them 0, so the output 0. If that means if it's x is equal 1, it's gonna be 1, so the output also is x. That means they're equal to each other, so this statement is correct. Make sense? Okay, so implementation. So we talked about this, but we haven't talked about implementation. If somebody tell you that f at a function of x and y and z is equal x ORed with y complement ended with z, and I'm asking you to implement it using the gates. So now you need to remember what the symbols, right? So in that case, how can I implement? I have an x and it's ORed with a combination of two things ended. So I have to have here what? And gate. Then what is those two things? We have z, we have x, but the y is not gated. So that means, you know, they're gonna be, and this is the function. Did you see what I did? So the implementation of such a kind of circuit is 3 gates. One is OR, one is AND, one is NOT gate. Maybe in a next lecture, I'll be talking about the response time of gates and how can we calculate delays. Okay, let me see what is the problem here. Yeah. Okay. Anyway, is it clear? So let's find some examples. Maybe you can find more examples. Okay. Imagine the following. Okay. Imagine that f as a function of x and y and z is equivalent to x complement y complement and z ORed with the x complement y and with z and x y complement. And I'm asking you is to optimize number of literals and decrease number of gates before you go and implement it. So we need to think about all the tricks we learned before, right? So look at it. So what we have here, we have something fun. We can take this as it is, x, y complement. Then we will notice something here. X complement is same here as x complement. Do you agree? And then z is there as well. So I can literally say that, you know, x complement with z ended with what? Y complement ORed with y. Do you agree? Now I can completely remove this to be equal what? What should be?
1.
1. So in that case, it's going to be x complement z ORed with the x, y complement. And this is basically my representation and optimization of the circuits I have as a Boolean algebra. Now, if somebody would like to implement it, that's not really hard, right? So I have an x, it has to be complemented, bring x complement, right? Then I have x is or ended with a complement of y. Those guys are like this, right? Then different color maybe, z is coming like that to be ended like this. Then those two guys will have to be what? ORed, right? So I can I can order it like that. And then I can write this is a function. Everybody agree? So now,
Professor,
yes, sir.
so quick question. Do you see how in the top you said X and then it became X complement?
Yeah, you mean this one?
No, on the graph. Yeah,
Yes.
yeah, we didn't do the same thing on the previous question.
Oh, you mean here?
Yeah, look at the Y.
Oh yeah, y complement here. Oh, sorry. Okay.
So do I have to say Y? Yeah.
You don't need. I'm just
that's
trying to
okay.
make it easy while you're working. You know, you don't need to say, but you know, it is
Oh,
good
okay.
because if you
Okay.
make a mistake, then you can get a partial credit. You know.
Awesome. Thank you.
You're welcome. So anyway, now let me find you more. You know, it's good to have more examples, right? Another example. If you have an X ended with the X complement Y, and somebody's asking you to go for implementation, what you gonna do? So you have to what? Optimize. So in that case, you're gonna say X like that is X, Y. This term is equal what?
0.
0. So say right X, Y. So it's gonna be what? An AND gate. Do you guys agree? Now,
Is it supposed to be X bar plus Y or X bar and Y?
which one?
For this example, like how you wrote the initial step. Okay. Yeah, that makes sense.
Okay, super. Let me find you another fancy example. I really like fancy examples. So here is one of the examples maybe I can give you. X, Y. I need to optimize this. What should I do? I can tell you a trick. What is the trick? Y ORed with Y complement is equal what? Right? X with X complement is equal what? So if I go ahead and say X, Y, S complements Z, Y, Z, and then end it to X, X complement, right? Let's go ahead and see how it's gonna look like. So it's gonna be X, Y, S complement Z, Y, Z, X, and Y, Z, X complement. So somebody will come and say, oh, Professor Ali is adding more terms. It's not actually optimizing, which is good, right? I don't like to optimize. So if you look at it, actually it looked really scary, but in reality it's not scary. I'm tricking. Why? Look, this term with this term can give you something cool, while that term with this gentleman will give you something even cooler. And then, you know, you will find everything now is getting smaller after that, right? So let's see. So if you go ahead and say, if these two guys, I would like to look at them, I will find X and Y are friends, right? So it's gonna be X, Y, and the two, one with Z. So we can say bye-bye Z, right? Then from there, we can take the X, Z, and literally we can come and say bye-bye Y. So the circuit from expanding it, I squeeze it as a sponge. So now it's X, Y, ORed with the X complement Z. Fun, right? So you need to learn to be a tricky. That's the whole thing. How can you be a tricky? Just practice. What is the final target? What is the outcome of today? Learning Boolean algebra, learning how to deal with the Boolean algebra by fully understanding the three basic gates we have at the moment, which is the OR, AND, and NOT gate. Later on, we'll have different gates, but those are the most important thing that most of the Boolean algebra are based on. And all of the tricks of the postulates of the entities helping us for optimization. Let me find you another example you will like. Okay, somebody will tell me, hey, Professor Ali, what do you think about this? All of them are ended together. Oh my gosh, that's gonna be a lot of work, right? You will multiply everything to everything, and from there you can make it small, right? Let's see how we're gonna do this. Sorry. So in that case, I can just go ahead and say x complement and xz and x complement y and yz, and that will be in the yz, right? So pretty much this is what arrivederci, bye-bye, we don't need it anymore. That's equal 0. And then, you know, we have those guys still will be multiplied to y and z and see what will happen, right? So let's multiply them. So that means it's gonna be x, y, z, x complement y, y, then you know y, y, z, right? Then x, z, z, x complement y, z, y, z, z, right? So for what I learned, this one nobody can touch, leave it as it is. So it's gonna be x, y, z, ORed with y ended with y is what? Y, right? So at the end of the day, gonna be x complement y, y ended to y, it's gonna be y, so gonna be y ended to z, then z with z, it's gonna be just one z, x, z, then you know this is still as it is, and then this one is gonna be y, z, right? Now similarities, yz and yz added to each other, what is the output? You can remove y and z and put it x. X plus x is what? Or x or to x. Exactly.
So YC.
YZ.
Exactly. So gonna be yz. So gonna be here x, y, z, or to x complement y. And here is y, z, no more this. And then, you know, we will look to x, z, and leave it with us. Is there any other way for optimizing from your point of view? I think there is. This guy gonna say bye-bye to who? To y. Right? Because, you know, I can come and say x, z, and you take y like this. Right? And then I can just say x, y, y, z. So then literally I have x, z, x complement y, y complement z, and pretty much using something called duality, you will find out that that will be x, y, or with x complement z. This is the equivalency of the whole entire circuit. Multiply this, you will get that. Sounds good? Let me find you more examples. Okay, somebody's saying that, I can complement the whole function and see what will be the output. So example for this, if f as a function of x and y and z is equivalent to x, y complement, z complement, y, z, like that. Sounds good? And I'm asking you to complement the whole function. So I'm gonna make a complement like that. So we're gonna use who? De Morgan, right? So in De Morgan, we have x complement, and here's and gonna be or, and then we have this block here gonna be completely what? Complement. And then that's completely complement. And then I can just go ahead and like this, and then I can say x complement plus z complement, right? And that will be ended with y complement. Do you agree? Then clear up this big mess. So it's gonna be x complement, and then here it's gonna be x z and the two y z complement. Then you're breaking up based on the Boolean algebra distribution thing. So it's gonna be x complement, and then you take those guys are gonna be what? X y complement, and they're gonna be x z complement, and they're gonna be y complement z, and they're gonna be z z complement. Sounds good? Now this guy is equal what?
One.
Huh?
One.
Let's try it. But remember, if z
0.
is equal 0, so they're gonna be what? 0 ended with 1. Output is equal 0. If z is equal 1, they're gonna be 1 ended with 0. It's still 0. So bye-bye this term, right? Now we have the function will be x complement ORed with the xy, ORed with the xz complement, ORed with the yz, like that. Is there any room for optimization from your point of view? That should be fine, I believe. That makes sense? If there is any room of optimization, that still will be great. I feel there is a room here. You can leave it like this, or you can optimize more. Okay? Let me find you more examples, actually. We just have 7 minutes left, so I don't want to start a new concept, so you guys will be kind of confused, So let me find more examples. Let me go in the back of the questions here and find you some questions.
Hey, Professor, could you show us what the diagram would look like for this one?
And this diagram will look like? Sure. So, you know, here, not gate x complement, right? And that will be ORed with x. Yeah, I have a feeling that it's gonna be more optimized, but you know, anyway. So if you have here y, so you optimize this to be y complement. I'm sorry about that. So you have y complement. That y complement, it has to be what ended with x, right? So you take it like that. And that will be the first term when you OR this together. Do you agree? Then you take this guy like that, and you end it with x and yz complement, right? So you need an end will go with you to be ORed like this, and will be out here, and that end will be the x and the z complement like that. This is not connect, right? Then you know you will take this and still you will end it, will OR it, I'm sorry. You will OR it like this with the end gate of the y and z, and that will be the function, right? I mean, I'm not that really great in drawing now, but you get the point. If you have a lot of colors, you're gonna do it in a fancy way, no? That makes sense?
Yeah.
Yeah. But other than that, you know, it's easy. I just need to give you one more example from the back of the problems. I will do it in front of you, and then we'll be done for today. Sounds good? Unless you guys have any lectures. You guys have any other lectures?
I don't.
You do, right? So if that's the case, don't worry.
No, for me, I don't. I don't know about the rest of the students.
What about the rest of the people?
This is my last one for the day.
Okay. So if nobody has, I will just try one more time, and then you know, we'll be done. Okay?
All right.
Let me find you something tricky. Yeah, that's a very good one. But still, you need to learn something. Okay, here. X, Y, Z ORed with and X, Y, Z complement. And what they're asking there, simplify the following Boolean expression to minimum number of literal. Okay, so that means we need to use the list number, right? And oh, by the way, this is not complement. So, okay, so if you look at it, it's very easy, right? This one and this one can be taken together, right? So you're gonna be X, Y, and then with the Z complement, and then you already have X complement Y here, right? Then this is gonna be what? Bye-bye. So you already have X, Y with the X complement Y, right? Then Y will be taken, and you already have X complement. End of the day, they're gonna be 1, so you already just have Y. So imagine all of this big mess is equal to Y. Life. Right? Do you want one more time? Or you're done? If you guys are done, I'm fine, you know?
Oh, by the way, Professor, I think the last one you could have optimized it. Or you were thinking you could?
I think I can optimize it, yes. This one,
Yeah.
optimize one more time. But
That's one of the rules.
yeah, there's the dual. You can use a duality, and from the duality, you can actually make it 3 terms. Maybe we can look at it again one more time next time, okay? But at least let me give you another one fast, and then you'll be done.
All right.
So here's A complement ORed with C complement, or ended with the A, B complement, C complement. what should we do? You're gonna start distributing, right? So gonna be A complement, A complement, B complement, A complement, C complement, then you know A, C complement, B complement, C complement, and C complement, C complement, right? This guy is 0, this guy is C complement, right? So you can write it as a C complement with the A, B complement, complement, A complement, C complement, and A C complement, and then you know B complement, C complement, right? Super easy lemon squeezy, because you know I can take this A and it's gonna be bye-bye. So pretty much I can write C complement to A complement, right? Then this gentleman and this one will do a good job. So gonna be a C complement with one E complement, right? Then we just have that guy by himself doing nothing, right? Now, you know, if you look at it, this is gonna be what C complement, and if you look at this one, it's gonna be what C complement. They're gonna be A complement, B complement. So pretty much this one is what C complement, A complement, B complement, and everything is complement. So basically, you know, if we look at it as a circuit, you already have an A not gated with a not gated of B. Then these guys will be ANDed, and that will be ORed with not gated C. And thanks so much for your time and your effort. And I wish you a wonderful night and stay safe. If you have any question, don't hesitate to book like, you know, a time slot during the Calendly or during the next lecture, and I will be more than happy to assist you. You guys have any questions? Everybody's happy? Perfect. God bless you guys, and thanks a lot. Stay safe. Talk to you later.
All right, God bless. Bye-bye.
Thank you.
Bye.
Thank you, Professor.
Bye.
Bye.
Thank you.